This is level 1 of the CFA program, the topic on quantitative methods and the reading on probability concepts. From my perspective, this is among the most important readings in level 1 because it provides us with a great foundation to apply these probability concepts to other financial decisions that we're going to make throughout level 1 and then of course level 2 and level 3. We're surrounded by probabilities, right? Every day we ask the question, what's the probability is it going to rain or snow? What's the probability that the train will be on time? What's the probability my car will take me to work? Probabilities, right? But as good financial analysts, we want to know the answer to these questions. What's the probability of a stock increasing by the end of the year? What's the probability of a bond defaulting by the end of the year? What's the probability of an option finishing in the money? And you'll see this kind of a sense of this general idea of probabilities and probability concepts as they can be applied to specific events. And that's really that first LOS there. But I want you to skip down to look at the third and the fourth. Describe probability of an event, calculate and interpret conditional probabilities. So all of the other LOSs are pretty much surrounding those two. We want to describe and calculate different types of probabilities. Now, of course, we're going to need to know some supporting information and have a good understanding of things like mutual exclusivity, empirical or subjective, and a priori probabilities, dependent and independent events. We're going to have to know some probability rules. And then as we begin the second page of the LOSs, we're going to advance over to portfolio theory when we talk about expected values and standard deviations. We'll look at probability trees. We'll go ahead and look at briefly Bayes' theory, and then we'll end with some counting issues that you probably learned back in 5th or 7th grade, whatever time period you learned about factorials. So let's go ahead and start with this relatively straightforward definition in the first LOS. So a random variable refers to any quantity with uncertain expected future values. Now, this is what I was saying earlier in the introduction. Rate of return earned on a stock next year, value of some kind of an index, or the time of death. So random variables, remember, and I always think of a random variable using that Excel function, the random variable function. If you hit that thing and you hit the enter, any number can show up in that particular cell. That's what a random variable is. An outcome refers to any possible value that a random variable can take, right? Time of death could be, 2040. For me, it could be S&P 500 increases by 22%. Rate of return on a stock could be 16% or minus 22%. And then event is a specified outcome or a specified set of outcomes. Let's continue on with this next LOS, which really is, let's look at some more definitions. So what does the term probability mean? A number between 0 and 1. And skip down to that third bullet point here. A certain event has a probability of 100%. This is going to be really important when we talk about this concept of a risk-free rate of return going forward to finish level 1 and then, of course, level 2 and level 3. I'm guessing you know that we use U.S. Treasury securities as a proxy for that risk-free rate of return. Well, what that means is that U.S. federal government, with 100% certainty, is going to make those promised payments. Now, that might be the only case where we have a 100% probability when we talk about financial securities and financial markets. Although when we talk about derivatives, and I show you some examples, there are opportunities out there to perfectly hedge, which means you'll have a 100% probability. But that's a conversation for a future day. If an event is impossible, then its probability is 0. The probability that my children collectively will enjoy tonight's prepared dinner, that will be 0%. So between 0 and 1 means that 10%, 20%, 50%, 80%. So we can define those probabilities between 0 and 1. So the two defining probabilities, any number between 0 and 1 and inclusive, and then of course the sum of those probabilities must equal 1 because something's going to happen, right? If you have a 20% chance of rain and an 80% chance of sunshine, well, there's a 100% chance of something happening today up in the atmosphere. How about mutually exclusive events? It means that only one of them can take place at any time. My example that I give students all the time, and this might resonate with you, is that the marital decision and the marriage event is a mutual exclusive event. When you say I do to that one individual, you're saying I don't to all of those other people out there. So event A, return on the stock equals 10%. Event B, the return on the stock is less than 10%. And we use that example so that you can understand that there is a definition in which events can cover all possible outcomes, and this is the term we use is exhaustive. And so look at this example down below. Event A, return is equal to 10. Event B, return is less than 10. And then event C, return is greater than 10. So that example at the bottom covers all possible outcomes. Now, different types of probabilities. An empirical probability results from analyzing actual historical data. And what you're going to do, and we'll do this pretty regularly throughout levels 1, 2, and 3, is we're going to take a look at some historical returns and use that as a basis to estimate what's going to happen during the course of next year. Of course, in my personal example, we could say something like, none of my 4 children have ever given a thumbs up to any prepared meal that my wife and I have made over the last year. So given that the empirical probability of tonight's reception is going to be probably the same as it always has been. Now, of course, there's a little bit of subjectivity in my personal example there, but let's make sure you can separate that. So subjective probabilities reflect personal beliefs or judgment, personal experience based, so that you say something like, all right, here we go. You ready? This is going to introduce the element of behavioral finance. Oh, I love this stock. Let's just suppose it's Amazon stock because it's been going up and up and up for the last, however many years. And so I love it for the next 20 years because my wife and I order something from Amazon 2 or 3 times a week, and the Amazon delivery man or woman is so happy and they're so delighted when they come to our front door, and I get this gift that's like Christmas several times a week. So I'm using my personal beliefs to kind of say something about the return on an individual stock that may or may not have any foundation in economic support. A priori probabilities are deductive and based on reasoning, which means we can take a look at the data and we can make some kind of let me go ahead and say it, some kind of a mathematical, maybe quantitative is a better word, decision. So there's an example. 2 applicants, candidate A, 70% chance. Then we can look and say, hey, you know what? Candidate B only has a 30% chance. Reasoning there, that makes sense. All right, how about odds for and against an event? So this is just going to be a ratio, and so look at the second arrow point there. Given odds for E of A to B, the implied probability is just a ratio of A over A plus B, and so then the same is true for against an event. And let's go ahead and do just a quick example here. This should make perfect sense. An analyst believes that earnings per share will range from 20 to 35 cents next year. The odds for the stock beating that highest estimate, 35 cents, are 1 to 9. So that tells us 1 to 9, that's probably 10 outcomes. So what is the probability that the stock will actually beat the highest estimate? So there's the 1 in the numerator and then the 1 plus 9 in the denominator. So that's 10%. How about a conditional probability? Oh, now we're, back here we just had some information, just basic information. But now let's suppose that we have some extra information. And that's what a conditional probability does for us. So it describes the probability of an event given that something else has already occurred. Let's suppose that we're trying to predict a conditional probability, or just the probability that a particular football team is going to win a game this Saturday if it's college, or this Sunday if it's professional. And so what we can do is we can look at the history and we can, kind of give some kind of a general probability, which is what, we've done up to this point in the recording. But let's suppose that these two teams are evenly matched, and that over the last 10 years, each team has won 5 times. So you probably would think, hey, you know what, that there's probably a 50% chance that either one of these teams is going to win this coming weekend. But suppose that the 5 times that team A won, it snowed or rained or had some kind of weather event. And the 5 times that team B won, it was sunny and it was beautiful. So wouldn't it be relevant? Wouldn't it be critical to our estimate of a probability of this coming weekend's outcome if we knew what the weather was going to be, right? If we knew the weather, then we would be able to predict much more accurately what that outcome would be. So here's some notation. We're going to say, look at so we have P open parentheses, A/B close parentheses. We read that as the probability of A given B, conditional on B. So the probability that a stock earns a 10% annual return, given that it has earned 9% in each of the 2 previous years, then we can use that equation right there to get that probability. All right, so remember I said in the LOS introduction we're going to have to do some rules. So here's a multiplication rule, and we're going to have to worry about whether or not we have a joint probability, which is the probability of 2 events happening together. Here's the example that we've come up with. Both, there's the key word in there, both gas prices and bus fare increase at the same time. So the multiplication rule states that the probability of A and B, so we would read that the joint probability of A and B is equal to the probability of A given B, which we just did on that previous slide, times the probability of B. So that's joint probability. However, what we need to be aware is if these two are independent events, meaning that they are not conditional upon each other, then the multiplication rule tells us that we just take the probability of A times the probability of B. Here's a good example that we've come up. A bag contains 16 blue balls and 14 yellow balls. 2 balls are drawn from the bag at random, one right after the other without replacement. What will be the joint probability of both balls being blue? Now, I was taught by a good math teacher way back hundreds of years ago to take a look at the question and see if you can figure out what the answer might be. Can you give me an estimate without knowing anything about probabilities? I mean, look, we have 30 balls right in this bag, 16 of them, and 14 of them are 2 different colors. So about half are each color in there. So if you pick out one and then you pick out another, half times a half. So this has to be around 25%, right? So let's go ahead and do the actual math, demonstrate the application. All right, so the probability that the first ball is going to be blue is, of course, 16 out of 30. But then, since we're doing without replacement, then we need to adjust this down to 15 out of 29. So all we do is take 15 out of 29 times 16 out of 30, which is it's almost like the 50% times 50% that I suggested to you before I showed you this gray box. So 27.59%. How about an addition rule? We need to make sure we're aware of mutual exclusivity. So if we have mutually exclusive events A and B, and there's a good box up there in the top right, A and B, so all we're going to do is sum those 2 probabilities. But for events that are independent or non-mutually exclusive, so bring those 2 circles in together so there's overlap in there, And what we don't want to do is we don't want to count the overlap twice. So the addition rule for non-mutually exclusive events is exactly what it was for mutual exclusivity above, right? Probability of A plus the probability of B, but then we need to subtract out that overlapping part of the two circles, so we just subtract out the probability of A and B. So here's a good question that we've come up. CFA candidate, probability that she gets the first question correct is 30%. Probability she gets the second question correct is 40%. Given the probability that she gets both questions correct is 10%, what is the probability that she gets the first, the second, or both questions right? So we're going to say A plus B, right? 30% plus 40%, that gives us 70% minus the 10%, right? So there's 60%. Compare and contrast dependent and independent events. So these are exactly what you might think. Dependent events are those that depend on each other, and independent events are those that do not. So look at our dependent event example down there in the bottom right. We just did this. If you draw a blue ball without replacing it, the probability of drawing another blue ball changes, right? That was what were those numbers back there? I might as well go back. Instead of the 16 out of 30, it becomes 15 out of 29. That should make sense there. Independent events, meaning that if you do something over here, it's not going to have an impact of over here, rolling the dice and flipping a coin. And there's the annotation that we use there in the middle. How about unconditional probabilities? This is also known as marginal probabilities. And marginal probabilities are going to become really important as we move through level 2 and maybe even a little bit in level 3 when we talk about correlations and causation. And we want to see exactly what that marginal probability of, some event occurring like stock price going up, etc. Probability that an event occurs without taking into account any other preceding event. So unconditional probabilities are not conditioned, right? And so we refer to those as standalone events. Probability that a stock earns 10% annual return without considering the preceding annual returns. Unconditional probability. Now here's another probability rule. Total probability rule explains an unconditional probability of an event in a series of mutually exclusive and exhaustive scenarios. So here we're going to compute the probability of event A occurring given some other stuff over here. So there's the notation, but let me go ahead and show you exactly what we mean here. So notice down the left-hand column, we have two states of the economy, no recession and a recession. So one is the complement of the other. There's that C in the superscript. So probability of no recession, 70%. Probability of a recession is 30%. And then we can go over and annotate the stock price performance, the rise and fall. So there's the slash given the complement or not. And so there's the associated probability. So what is the total probability of a stock rise? So here we go. All we're going to do is take, this is really just a weighted average. So we're going to take the 80% of the probability of an economic state, right? So 80% of 70%, and then we're going to add to that the 30% times the 30% of the probability of that stock performance if it goes up, and then the probability of that economic state of 30%. So we get 65% there. Let's move on to what does all this stuff mean when we put together a portfolio? Because we're going to have, if we have, let's just say we have a 3-asset portfolio, we're going to have asset 1, asset 2, and asset 3. Each of those assets is going to have its own outcomes, right, based on states of nature. So they're each going to have expected values, and then they're each going to have their variability around that expected value. So we want to calculate the mean and standard deviation. So this LOS asks us to, hey, apply a little bit of this probability concept that we've just learned to portfolio analysis. So I'm going to just go ahead and read this very first arrow point. Expected value of a random variable is the probability weighted average of the possible outcomes. All right, so think of probability of x times x1, or x1 times x1. There is the expected return on a portfolio based on probabilities and each of those outcomes occurring. For individual stocks, then you can add it. You can add it to portfolios of stocks. And then the variability around that expected value, there's the formula for variance, and we're just going to take the square root of the variance to get the standard deviation. And what we're doing is we're taking each possible outcome, there's the x, minus the expected value of x, which is the mean, and then we're squaring it, and we're squaring it as my students always tell me, to get rid of the negative, and that's true, but we're squaring it to get rid of the negative. So, and there's a comma after that, and the students don't ever give me the sentence after the comma. The comma after it tells us that what we want to do is make sure that the minus numbers don't exactly offset or offset at all the plus numbers. So we square it to get rid of the negative. And look at that last arrow point. Standard deviation is easier to interpret because it is in the same units as the random variable. Yes, remember, the variance is a squared term, and your husband or wife or your most important person in your life doesn't ever tell you to stop at the food store on the way home and get 12 squared pounds of potatoes or some other kind of crazy kind of a suggestion. So we take the square root because it makes sense, right? Easier to interpret, but it makes sense. All right, so let's go ahead and use this into the LOS that asks us to calculate. So we've got probabilities down the left-hand side. Remember, what did we say earlier? Those probabilities must sum to 1. So 20 and 30 and 50, that gets us 100%, right? And so here are the sales. So we have a 20% chance of having 50 million. We have a 30% chance of 40 million and 50% chance. So what is the standard deviation of sales? And this is kind of a trick question because before you can compute the standard deviation of sales, you have to compute the expected value of those sales. So all we're going to do is multiply column 1 by column 2, right? 20 times 50, 30 times 40, 50 times 30, and we'll sum those. So that's a probability weighted average, and we get 37 million. Now, what we need to do in order to get the variance of sales or the standard deviation of sales is that we need to go ahead and take each possible outcome. So 50 is our first outcome minus the expected sales. What was that, 37 in that previous one? Yeah, minus 37. We're going to square it, and we need to multiply it by that probability of 20%. And we do that all the way out to the end. Sum all those, and we get 61 million, and we take the square root, and we get around 8 million. So we have, you ready for this? We have an expected value for sales of 37 million. Now, the way we interpret that as good financial analysts is that of all the possible outcomes in millions of dollars of sales next year, the most likely, you ready for this? The highest probability of occurring is that 37 million. Now, of course, we want to ask ourselves the question, all right, if we say we expect to get 37 million, let's follow up with, well, how wrong can we be? Can we be this wrong or can we be this wrong? That's what standard deviation tells us. It's a measure of risk. So on average, we're going to be about $8 million off on our estimate. That's That's what standard deviation tells us. See, the 61 million is a squared term. So if you say 61 million is the variance, at least I'm scratching my head saying, I'm not quite sure what that means. Take the square root. Now we know that when we expect 37 million, we're not going to be surprised if the actual sales next year is, let's say 8 above or 8 below. Now we'll go ahead and talk about confidence intervals at length, and we'll need that standard deviation to do that. But that's a conversation for another day. All right, how about conditional expectations? All right, so the expected value of an investment given certain set of real world events. So this goes back, of course, to my football example. Real world event is it snowing or sleeting or raining, or is the sun shining, given a set of certain real world events. So, of course, the expected value of an investment is impacted by lots and lots of these real world events, like what kind of new product lines is our competitor introducing? What does the government say about our decision to take over another company? Do we have a monopoly? Is the government going to come in and offer up some kind of a lawsuit for antitrust violation? Or are institutional investors, like financial institutions, are they going to be required to increase their reserve requirements or decrease their reserve requirements from a government mandate? Or how are these financial institutions going to react? All of those events, right, real world events, are going to impact. So what do we say there in that third arrow point? Total probability rule is very useful. So there's the unconditional expected value is the sum of the conditional expected values. So let's take a look at an example. 20% chance that the government will impose a tariff on imported cars. All right, so a company that assembles cars locally expects 14% return if the tariff is imposed, 11% if the tariff is not imposed. What is the unconditional expected return? So once again, this is just a probability weighted. So we have a 20% chance of getting 14, which means, there's the implication, right? An 80% chance of getting 11. You take a weighted average and you get somewhere around 11 and a half. This is one of my favorite slides because we are going to use this again and again and again, especially in level 2, especially when we have a discussion on derivative securities and maybe option pricing and maybe even swap valuation and maybe some other things out there. But let's go ahead and look at a tree diagram. So we start here, time period 0, right? That's the over there on the left. And then we branch and we say something like, you know what? Of all of the possible outcomes, let's suppose that we break it down into 2 so that we can say something like, hey, you know what? Something's going to happen up here and something else is going to happen down here. The example that we've come up with in this slide is tossing a fair coin twice. Fair meaning that I guess it's a heads or a tails, and it's not weighted some way, or so that the flipper can increase his or her probability of an outcome. So a fair coin toss. Those of you who are football fans, I encourage you to go look up the Jerome Bettis coin flipping event in the playoff game. I don't know how many years ago that was. 10 years ago. It's super funny. All right, so note what we have. We can flip the coin, and we have a 50% chance, there's the 0.5, 50% chance, there's the 0.5 of it being a heads or a tails. So this is a tree, right? So there are the branches. And then if we flip it again, we're going to do the same thing. And we have those equal 50% chances. And so look on the middle columns out there. So what is the chance that we have 2 heads? What's the chance that we have 2 tails? What's the chance that we have heads then tails? Or tails then heads. So these are all of the possible outcomes. And this is a visual representation of flipping a coin. And of course, those probabilities all have to be 25%. But you knew that at least before, maybe before even watching this slide deck, but then that example that I gave you 50% earlier on. All right, so look at the very bottom. So first toss, second toss, there are the outcomes, possible outcomes, and then the probabilities. All right, let's do a real live example. Suppose the prospects for recovering a principal on a defaulted bond issue depend on which of two economic scenarios prevail. So scenario 1, probability of 60%, which means scenario 2 has a probability of 40%. So that scenario 1 will will result in a recovery of 80 cents. Now that's per $1, right? With a probability of 35. 70 cents with a probability of 65. All right, so scenario 1, we've got a couple of probabilities layered in there. Scenario 2 has a probability of 40%, will result in a recovery of only 60 cents with a probability of 70, and then 30 cents with the probability of 30. So what is the expected recovery closest to? So here's our tree, our decision tree. So we have 60% going up, 40% going down. And then we hit scenario 1 and scenario 2. Then we have different probabilities, right? We have 35% and 65%, then 70 and 30. So there are the recovery amounts. There's the 80 and the 70, the 60 and the 30. And so all we're going to do is we're going to estimate the recovery today, expected recovery today. So we're going to take a weighted average probability of that 80 and that 70. So 35 and 60, that gets us 735. And then scenario 2, there's 70 and 30, and we get 51. So that was based on those probabilities out there on the right-hand side of the tree. Now we have to, I'm going to say discount, but that's really not the right term. We're going to assign those probabilities of 60 and 40 before we know which scenario actually occurs. So we get 645. Let's go ahead and continue our discussion on portfolio returns. So look at this LOS. Calculate and interpret expected value, which is a mean, variance, standard deviation, covariance, and correlation. So we have lots and lots of random variables that are going to go inside of this LOS. So let's go ahead and start with a simple one. Calculate the expected return on a portfolio. Now, of course, the expected return on a portfolio depends on what is the expected return on each of the individual securities inside of that portfolio. For example, if we have 3 stocks in our portfolio and the expected returns are 20, 25, and 30, no matter how we weight them, the expected return on that portfolio is going to be between 20 and 30%. But if we have 3 treasury securities and the expected return on each of those is, 1, 1.5, and 2, no matter how we weight them, we're going to get between, 1 and 2%. So the W in the formula is the proportion of dollars or currency allocated to that individual stock. So let's go ahead and read that circle point. It's a weighted average of the expected returns on the component securities. So if we have 3 assets, let's say asset 1, 2, and 3, they have expected returns of 10, 20, and 30%. Well, the expected return on the portfolio is going to depend on how we allocate. All right, so this is an asset allocation question. What is our weight 1, our weight 2, and our weight 3? Now, of course, those weights have to sum to 1. And so what did I say? If we have 10% in weight in asset 1 and 10% in asset 2, that means we're going to have 80% in asset 3, which was the highest of the 3. So we're going to have a higher expected return on the portfolio. So before I go on, remember that the expected return on the portfolio depends on, which kind of assets you have, and then how you allocate your wealth across those assets. Now, the variance of the return on the portfolio is really kind of a cool function. And back in the old days, when I would teach this to my MBA investments class, I would take my students through all the steps, and I would come up with this equation there that's in the gray, and I would say, here it is, and the students would say, what, Jim, do we really need to know all that stuff? And my answer, of course, was yes, of course. The more you can cram into your brain, the better off you are. But let me just go ahead and tell you what I tell my MBA students now. I say, hey, look, remember back when we did the variance of the returns for an individual security, we took each expected outcome minus the mean outcome, and we squared it. Remember, we squared to get rid of the negative. Well, if you put this equation there inside of that expected return formula and the standard deviation formula, you get lots and lots of subtractions and then lots and lots of squares. And when you cancel and collect terms and you do a bunch of algebra, this is what you get. All right, so the variance of a 2-asset portfolio is not the weighted average of the standard deviations or the variances of the component securities. And so that's the important first lesson here. So what we're going to do is we're going to take the weight in the first asset, or asset A in this case, and we're going to square it, multiplied by the variance. And then we're going to take the weight in the second asset, and we're going to square it, multiplied by the variance. And so that takes care of, all right, I want you to look on the right-hand side of the equal sign and then to the left of the plus sign. That takes care of the weighted individual riskiness of asset A. The next thing to the right of the first plus sign and to the left of the second plus sign, that takes care of the weighted riskiness of asset B. So you have the variance of a portfolio depends on the riskiness of A and the riskiness of B, and then there's a plus sign over there. And I always tell my students to think of this as the co-riskiness, because A and B do not operate inside of a vacuum, right? What do we know? When you go to the floor of the New York Stock Exchange, that stock returns and stock prices tend to move in the same direction. So if everyone's happy and all stock prices are going up, then one individual stock is probably going up as well. So we need a measure of that co-riskiness, and that's what we've written up there on that circle point, right? So the variance of a portfolio's return is a function of the variance of the component assets, I just did that for you, as well as the covariance between each of them. So over on the right-hand side, we have plus 2 because A covaries with B and B covaries with A, not because there's 2 assets in the portfolio. So the 2 is because A and B and A covariate against each other by the same amount, so you multiply it by 2. Then we multiply by the weight in A, then the weight in B, and then we multiply by that covariance term out there. So let me go ahead and give you some introductions to covariance. Covariance is a measure of the strength and the direction of a relationship. Think about it this way. If we have stock A and stock A does this, here it is in time period 0, and here's stock B in time period 0. If stock A moves like this, stock B could do a bunch of things. It could go backwards. It could go forwards a little bit. It could go farther. It could go over here to the side. I don't know if it could jump over here that way, but it's going to measure, covariance is going to measure how B reacts to what A does. So we get the variance using that formula, and then we just take the square root of that variance to get the standard deviation of the portfolio. So let's go ahead and take a look at an example, right? Here we have 2 mutual funds, A and B, 60% invested in A, 40% invested in B, and the covariance is given as 1.44%. So further information, we've got the expected return on A and B is 15 and 10%, and the standard deviation is 20 and 15%. So what we're going to do is ask the question, what is the expected return? So the expected return has to be between 15 and 10, right? Standard deviation of returns, you're tempted to say that it has to be between 20 and 15%. However, I want to caution you. It's probably never going to be greater than 20%. I can live with that. But it might be less than 15% depending on the degree of covariance up there. Well, let's see what happens in this example. So there's our weighted average. So all we do is take 60% of 15 and 40% of 10. That's a simple weighted average expected return. So what did I say? It had to be between 10 and 15. There it is, 13%. But for the portfolio variance, let's make sure we go through this correctly. And please don't make the common mistake that some of my undergraduate students do. My MBA students don't do this too often, and I'm hoping that you won't do this. Don't forget to square those first four numbers, right? 60% squared times 20% squared, plus 40% squared times 15% squared. The last thing that you want to do on the exam, in the stress, you're under time stress, and you go through and you forget to square one of those. So take a deep breath and take your time. Make sure that you do this. And that's my advice all the time. In fact, next time you watch an NBA basketball game, watch one of these dudes, or the WNBA, watch one of these women. They get the foul shot, and what do? They take a dribble or two. Hey, take a deep breath. This is what you got to do in these kinds of problems. It's long mathematical stuff. So take a deep breath and make sure you go through your routine and you follow through so you can make your foul shot. So we get about 2.5% for variance. Take the square root of that, and you get 15.78. So what did I say to you back here? It's the standard deviation of the portfolio. It's not going to be greater than 20%. It might be between 15 and 20%, and that's the case in this example, but it might even be less than 15% because of the beauty of diversification. Now, remember what I said? I went like this. In this case, the covariance was, 1.44%. So when A went like this, B moved in the same direction. But suppose that when A goes like this, B moves in the opposite direction so that the covariance is negative. Just for fun and giggles, put a minus sign in front of the 0.0144. Then you bring the minus sign out, and that turns the plus sign into a minus sign, and you're going to get a much lower variance. Take the square root of that, and you're going to have a standard deviation of, let me make up a number, 12% or 9% or 11%. That's the beauty of diversification. We'll talk about this at length as we go through levels 1 and 2 and 3, but diversification depends on the covariance between those two assets. All right, here's the formula. So calculate and interpret covariance and correlation coefficient. So what I want you to do is look at the formula for variance. I copy and pasted that from an earlier slide. So if we do the variance, all we're doing is taking each possible outcome y minus its mean, and then we're squaring it, right? I just left that term over there. So y minus the expected value of y times y minus the expected value of y. That's squared, right? Well, the covariance between x and y is very, very similar, but instead of the variance where we're squaring it, and essentially we're saying in the variance formula, we're saying, hey, how much does y vary against itself? We call that the variance. But with covariance, now we're saying, how much does x vary against y? So there's the equation for the covariance. We take each possible outcome for x minus its mean value, and we multiply that by each possible outcome for y minus its expected value. So look at the example we have in that second circle point. We might be interested in the degree of co-movement between interest rates and inflation. Oh my gosh, that makes perfect sense. Now, of course, what we can do is that we can throw probabilities in there, and you shouldn't be surprised that we're going to throw probabilities in there. And this is just going to be a probability weighted covariance between the assets. So this equation here and that equation right there, they're the same equations, but instead of x's and y's, we use the notation. Here, look at the second circle point. If we have two assets, I and j, with returns r sub I and r sub j, so we're taking r sub I minus the mean of r, and then r sub j minus the mean of j. And then notice that right there in the middle, we have the probability of each of those possible outcomes, right? So let me read those bolded points up there. Based on the probability weighted average of the cross products of the random variables deviations. Okay, that makes sense. So let's go ahead and take a look at an example. We have economic growth. So two choices here, less than 4, greater than 4. We have 40% and 60% chance. So return on stock A and return on stock B. There's the table. We've seen a couple of tables like that before. What is the covariance of returns? So here is an explicit example of how we're going to do this. But first, we need to do the expected return on each stock. So stock A, we've done this before, right? We get 572. Stock B, we get 4.40%. So then, going down that second column, we take each outcome, 2.3 and 8, subtract that from 5.72. There's the mean that we just calculated. And in column 3, we take each possible outcome, 6.5, and 3, subtract that from 4.4%, we get the -7 and -3, multiply that by the probabilities. So make sure you go back here, see those probability, the P of R sub I is, and close parentheses, that doesn't come in until the end. And then you get probability weighted product. So the covariance is 4.79%. Calculate, so we just calculated. How about interpret it? Let's interpret it. So the minus sign tells us that when A goes this way, B goes in the other direction. Now, not all the time. Now, that doesn't mean that every single day that there's going to be that inverse relationship, but on average, right, and we're weighting the averages by that probability, on average, that sign is negative, which means they tend to move in opposite directions. This is what I just said, right? Positive covariance returns on both assets tend to be on the same side, right? Negative. And zero covariance means that when this thing goes like that, then this thing could do anything. It could go back, it could go forward, it could go sideways, it could jump up, it could do anything. I mean, it's not going to do all those other things, right? But the idea of a zero covariance means that the two assets are independent, and the reading uses the word unrelated, which means that when one does something, you really can't predict what the other one will do. Now, remember what I said just a few moments ago, that the variance is a squared term, and you never buy 12 squared pounds of potatoes at the food store. Well, I did say to you that that's a difficult number to interpret. Well, covariance is similar in that, because even though you're not squaring the number, right, you're multiplying it by another number. So it's kind of squared. It's not really squared, but it's kind of squared. And so here's what happens with covariance. When you compute the covariance between any two random variables, you can come up with almost any number, like, a plus 16 million or a minus 400,000 or 0.00052. And so just like we had written in an earlier slide that variance is difficult to interpret, so is covariance. So statisticians are super smart. And they say, okay, if we can't really understand what the absolute value of a covariance term means, why don't we standardize it? So think about what I said. I've done this before on slides, is that, the covariance can be any number. Can you see my hands way out here? But what we're going to do with the correlation coefficient is, if we take the covariance and we put it in the numerator and we divide by the product of the standard deviation of each of the two individual returns, what we're doing is we're putting covariance into a vise and we're squeezing it, and we're squeezing it all the way down to some palatable range, right? Covariance can be almost any range. Correlation coefficient can be -1 or +1 or anything in between. So think of the correlation coefficient. Think of it as the ratio, right? That's the definition of covariance divided by the product of the two standard deviations. But I want you to think about it as a standardized covariance. And that means that it's going to be between a -1 and a +1. So this gives us a better sense of, when one goes like this and one goes like that, exactly what that means. A strong positive linear relationship indicates a perfect linear relationship, which would be 1. So if we have a correlation coefficient of 0.9, that means when A goes like this, that on average, B is going to go 90% of the way. Now, don't ever tell a stats professor that I said that, but that's a vague interpretation over time. In other words, if the correlation coefficient is a -0.8 and A goes like this, that means B is going to go 80% in the opposite direction. So now we can wrap our arms around correlation and say magnitude and direction of a relationship. And of course, zero correlation. I mean, look, if covariance is 0 in the numerator, then correlation has to be 0, right? No linear relationship. All right, so let's go ahead and take an example, interest rates and inflation. Historical data 5 years, covariance is a minus. Standard deviation is 5.5 and 12. So calculate and interpret. So all we have to do is standardize that covariance term by multiplying by the product of the two standard deviations. So since the covariance is minus, has a negative sign in front of it, then correlation coefficient is going to have that same minus. So what do we say first is that, hey, when interest rates go up, inflation goes down, or vice versa. Remember, correlation doesn't tell us anything about causation. And now it's 0.11. So that's relatively close to 0. So we're going to say that that relationship, while negative, is not super strong. So what do we conclude there at the bottom? The interest rate and inflation are negatively correlated with each other, but it's not super strong. If that turned out to be a minus 0.91 or 0.81, then we would say, oh my gosh, these two things are super related. Now the reading shows what's called a covariance matrix. When I was in graduate school, my professors called it the variance covariance matrix, and I'll explain that to you here in just a second. And notice that we have color-coded these things. So we have asset A, B, and C going down the first column, and asset A, B, and C going across the first row. So I want you to look at the two reds. So the covariance between B and A has to be the same as the covariance between A and B. So the two reds are the same. So the covariance matrix is really a mirror image of each other. Same thing with the two greens, right? The covariance between C and A has to be equal to the covariance between A and C. And then, of course, the purples between B and C as well. Now look at the blues going down the diagonals, the covariance between RA and RA. Well, we could rewrite that. That's the variance of A, and then the variance of B, and then the variance of C. So notice the second arrow point, a 2-asset portfolio would have a similar 2-by-2 matrix. All right. What you can also do, look at that last circle point, a correlation matrix can be created to represent correlations between and among the various assets. All right, let's get back to conditional probability. So what was that example that I gave you that we were trying to determine the outcome of a football game this weekend, and the two teams were evenly matched, right? But what we found out is that even though they're evenly matched, one does better in the snow and sleet and rain, and one does better in the sunshine. So we call that a conditional probability that, hey, wouldn't it be awesome if we knew what the weather was going to be like the instant before the game started? Then we could update our probabilities. Well, that's what Bayes does. And this goes back to, I want to say 1770s or 1780s. So the reason that I mention that to you is because it's fascinating that, stuff that happened hundreds and hundreds of years ago, the CFA Institute think is still important today. So look at that first point there. Bayes' formula is used to calculate an updated posterior probability given a set of prior probabilities. All right, so the Reverend T. Bayes, 1775 or whatever year, widely used Bayesian methods of statistical influence. So notice that third point there. It allows us to turn around conditional probabilities. And I like to think of it as this is taking new information and adjusting the probabilities. Like if it's Wednesday and the football game is going to be played on Sunday, well, we can compute a conditional probability of an outcome based on, the relative strengths of two teams and the Wednesday probability of a snow event or a rain event or a sun event that coming Sunday. But still, we're estimating that probability with some degree of uncertainty. But now, as we get closer and closer to the game time, we can update those probabilities. And that's what this Bayes formula does. And there it is shown in the gray box down there. So So let's go ahead and take a look at these probabilities here, or the notation. PE, these are prior probabilities. The event A is some event known to have occurred, and the probability of E given A is the posterior probability. So let's go ahead and take a look at an example. Let's suppose we want to get to work on time. So we have trains, number of train journeys, 50% New York, 30% Vegas, 20% DC. So we have crazy work schedule, right? Probability of a train arriving late in New York, Vegas, and Washington are 40%, 35, and 25%. So the first thing you need to do is shake your head and say, oh my gosh, why aren't these probabilities of the train arriving late like 1% and 2%? All right, so here's the question. If the engineer picks a train at random, what is the probability that it terminated late in New York? All right, so let's work our way through some of this notation. So N is the event, a train chosen at random terminated in New York. V is the event, a train chosen at random terminates in Vegas, and the same thing for W. All right, so we'll let L be the event, a randomly chosen train arrives late. But remember, look at the top. We're looking for the probability that New York is going to be late. So all we do is go back here and extract these probabilities. So in the numerator, we're going to have 50% and 40%. And then in the denominator, in this base formula, we're going to sum a couple of those probabilities. Of course, the numerator, 50% times 40%, and then the other two trains, 30 times 35 and 20 times 25. So we get a little more than half, right? 56%. Now, how about these counting problems? So these counting problems involve determining the exact number of ways two or more operations can be performed together. And so look at the example that we've chosen. So we can choose 7 stocks, 3 small cap, 4 large cap from a group of 50 stocks. So think about this. You got 50 stocks, in this big bag, and we're going to reach in and we want to choose 7 of them. Right? How can we determine the number of countings? So there's some good issues here. So let's go ahead and start with this n factorial, which I think I said in the beginning of the slide deck. I learned in 5th grade or 7th grade, whatever grade that was. But all we're going to do, n factorial, it just simply means that we're going to start with that number and multiply itself by every number that comes before it. On the timeline. So look at the example there. 3 factorial is simply 3 times 2 times 1, which of course is 6. And there's the location on the BA2 plus for the factorial. Let me go ahead and grab my favorite calculator. Look under the 3 button. There's a blue N. You guys see that? So if you want to go ahead, and those of you who have the 12C, you can do that n factorial. Labeling is interesting in that it's going to allow us to assign group labels k times to a total number of items. So look, we have n1 and 2 and 3 all the way out to nk. So what's going to happen? We want to categorize n items into k groups where we have some predetermined information. And so all we're going to do, there's the equation there, n factorial over all of those n's multiplied. So let's go ahead and do an example here. 10 stocks. Suppose your wish is to assign 3 different labels such that we have high-risk stocks, medium-risk stocks, and low-risk stocks. And, on the exam, you probably, at least I would do this, it's probably likely that you might read a sentence that says something like, high risk, medium risk, and low risk is determined by, hey, what did we just do? Standard deviation of those stocks. Or maybe we want to use beta as we move along. All right, so there we go. We're going to take the 10 factorial, right? There's our 10 stocks, and then we're going to divide by, well, we have 5 high-risk stocks, so there's the 5 factorial, and then 3 medium stocks, there's the 3 factorial, and then the 2 low risk stocks. So there's the 2 factorial. So if you do all that, I mean, in the numerator, you do 10 factorial, you get some gigantic number, right? Divided by a little bit less of a number, you get 2,520 ways. Now, you can combine all different sorts of securities. And let's go ahead with the added assumption that the order does not matter. So what we're going to do, once again, is take the ratio of factorials, but we need to subtract something in the denominator. So let's take a look at a quick example here. How can we choose 3 stocks from a portfolio consisting of 10 stocks? How many ways can we choose? So there are the steps in the BA2+. So all we're going to do is take the 10 factorial, right, and divide that by the 10 factorial minus the 3 factorial times, so you get 120 there. Permutations. Let's suppose the number of possible ways where the order is super important. So all we're going to do then is take the factorial divided by n minus the R, which is the R items. So let's do 3 stocks from a portfolio consisting of 10 stocks in order to execute a sale, but the order of the sale is paramount, so you get 720. So what do we get on this one back here? 120, but now we get 720. So here's the good question here. I would take a picture of this and put this in my camera, not my camera, in my phone, under level 1 slides to memorize. So this is a good one to help you read the question stem. So as you're reading the question stem, if you're asked to do some of these things, then this slide deck will tell you what to use. And that takes us through all of these. Boy, I'd love to pick out one of these that's super important. But I will say that I really like just exactly what I said, calculate and interpret conditional probability. So in order to do that, you need to understand the first 3. And then, of course, look at that one in the middle, expected value, variance, standard deviation, covariance, and correlations of portfolio returns. That's important moving forward.